she was smashing it on.
Okay, so we've got 1, and then we do a couple more 1s. I don't want to make this too big yet. And then we just keep adding 1s on the outside of the pyramid or the triangle, right? So we keep adding 1s. There's nothing weird going on here. And then once we get some space opening up, what do?
Add the number because the 2
We
is
start like
covered.
adding kind of diagonally. So we couldn't do anything there, so we've just got 1s. But now we can go like this and say in the middle we have 2 because 1 plus 1 is 2. And then if we add another 1 here, we can say that this is going to be 3 because 2 plus 1, and this is going to be 3. So do you need to memorize this triangle? No, it's like super easy to like just write it down. You know, it's not like something you need to memorize at all. You can if you want, but so then you just keep adding some 1s, and you see what happens next. So you go 1 plus 3 is 4. You just got to make sure you kind of have enough. So I like to use these little lines to keep track. So I'm not missing 1 or adding an extra 1 or something, you know? Let's do 1 more row. You can keep going as far as you need to until you get to the specific row that you need. So how do you know which row you need? Well, we'll talk about that. This one should be
5, 10, 10, 5. Then it's 6, 15, 20, 15, 6, and then it's like 7, 21, 35.
And there's patterns here. You
Stealing
guys
the
can
number
see the
from me.
patterns, right? Like there's like sequence patterns in here, isn't there?
3,
From
6,
like,
10.
from like the sequences that we did earlier. So you can see patterns in the triangle. But I mean that's plenty. That's good for now. Okay, you'd make it until you find a spot that you need to do your particular expansion. Because isn't that what we're going to do? We're going to expand this out. That's what this is called. In fact, it's called a binomial expansion technically. There's different ways to do it. This is the easiest way, I think. So this is all we're going to do. This is all we need, okay? So that just gives us the coefficients. Then we're going to have to do one other thing. So which row are we going to use if we're going to expand to the fourth
row.
So the fourth row?
Well,
so like 1, 2, 3, 4?
no, the first row doesn't count because that's a 0. The first row is 0.
Is that right?
Because the first row is 0.
Wouldn't it be easy to get this mixed up?
Yeah, the first row, because the first row is 0.
Yeah, so you can remember like a rule. I'm sure Mr. Parks gave you guys a rule
You
to
taught
remember.
me this in math class a couple weeks ago.
Good. So there's a rule you can remember, but I forget rules. You guys ever forget rules? I do. So I like to think of just finding one that I know for sure. And the one that you should kind of know for sure is this one. Let's just recall, if you needed to, let's go over here and go x plus 2 squared. Can you guys help me do that? We could write it out twice, right? There's a shortcut formula. Calm down. There's a shortcut formula, right? Can't you go x squared, and then the last thing is going to be 2 squared, or 4, and then we all remember that that's not all, right? That's that fundamental mistake that we can't make. There's other terms. There's going to be 2 other terms, in fact. But there's a shortcut formula. You've heard that before, right? The shortcut goes, if you've got a binomial that you're expanding, and it's just to order 2, you multiply these together, and then you go an extra times 2. That's the shortcut formula. You know what I mean? Have we heard that before?
I always thought it
Like
was...
to do those fast, I don't like to write it out twice. I say first thing squared, last thing squared, 2 of x times 2. Does that make sense? That's the shortcut to do those really fast. So let me use red to clarify here. So you go first thing squared, last thing squared. Those both have a what in front of them?
No. Then you put a 2 in front of...
Then you go 2 of the middle things.
Yeah.
So the middle things were 2x. Look at the red. 1, 2, 1. Where'd that come from?
Right there at the top.
Like what?
Came from right here, yeah? So I think if you remember that shortcut formula kind of has like a 2 in the middle, you'll remember this is for expanding what? What kinds of things? That's for expanding quadratics. And then you can say, oh, that's quadratic, so this next one must be cubics, and this one must be fourth degree like the one we want. You guys see what I'm saying? I think that's the easiest way not to mess this up. Is remember that 1, 2, 1 row is for what that we studied? Quadratics, parabolas. Okay? And then you can just go from there wherever you need to. Because you're always going to go beyond that. So, okay, so we're going to use this row. So this is fourth degree polynomials. That we're going to use it for. Okay, questions so far? So you guys I didn't see a lot of people that seemed familiar with this little shortcut formula. So I'm going to start doing that from now on, and then we'll get more and more familiar. Every time we see something like this we need to expand, I'm going to go first thing squared, last thing squared, 2 of the middle things multiplied together, okay? And you guys will start doing that too. All right, so for this, we're going to use that fourth row. So we're going to say the coefficients are 1 and 4. I'm going to have to erase it. And 6 and 4 and 1. Yeah? There's our coefficients. But you're saying, well, what about like the x's? How does that go? Well, it's really easy. Just like we did on this simple one, how did we start over here?
Squared.
We went the first thing squared because that was squared, right? So how are we going to start this? That first thing to the 4th power. Let's use some different colors. Oh, let's see. Go red and green even though it's not Christmas. First thing to the 4th. How many x's do you think this has? Go down. Descend. Descend. And this one technically has an x to the 0. Do we really need to write that though? Just like this thing in the end, did it have an x on it? No. Okay. So we're done with the x parts. And then for the y parts, how can I do that? Anybody have a suggestion?
Reverse it.
Reverse it. Why reverse it, Derek? We'll go back to this, yeah?
Yeah.
Didn't we start over here and say that thing squared, that thing to the 2nd power? So we're going to go that thing to this power and put it over here. And then, this is what Katie was doing. And then this technically has a y to the 0, but that's 1. Okay? So then you put pluses and you're done. There we go. And it looks crazy because it's in different colors, but if we expanded that out and wrote it down 4 times and combined like terms and took, 10, 15 minutes here and hoped we didn't make a mistake of trade, that's what we get.
That's what trying again.
Neat, huh? You guys want to try another one? I think we should do one more. Then we're going to do something else. Evan?
Does it work all the way down? Has anybody tried it like 15?
Oh yeah. Oh yeah. I mean, would it be hard to have a computer do this?
Yeah, well,
I think maybe in geometry next year that might be a good problem for us. On our calculators, we can write little simple software programs. We can actually make them pretty intense. Brandon Slade's older brother, used to write some pretty intense software to make his life easier in calculus and stuff. You don't have to, but he thought it was fun. Maybe next year we'll write a program to do this for us, so we could do like to the 20th power, and it just pops it out for us. That might be good. Good question. All right, let's try one more. So, let's see. We try that one. So what's a little bit different about this one? Can you guys tell me?
There's a 2 in front of it.
There's a 2 in front of it. That does make it a little trickier, but not much. If you're careful, it's about the same. I mean, it's not much harder. You can put a 2 on that. You could put a 7 on the y. It's still not going to affect it very much. Let's just do the 2 right now so we can see its effect. Okay. So coefficients. Let's keep the same color scheme. 1, 3, 3, 1, right? From the triangle a second ago. Let's make sure you have enough space. We have lots of space. I want to leave too little of space and then try to slam them in there. Okay?
Slam!
First term. What are we going to put here? Ah, so Kyle's already like going ahead, right? He's like already expanding the 2 out. He said 8x cubed. It's not 2x cubed? Good. But technically, I'm going to write it down. I'm not as quick as you sometimes, Kyle. I'm going to go, how about 2x all cubed, which is 8x cubed. We'll take another step. Good. And this one's going to be?
2x squared plus 2x.
And then 0 power, so not
then
there.
It's going to be y.
Where, here?
No. That's y. It's y squared. And it's y cubed.
I always have trouble doing it that way, so remember, when you do this, what I'd recommend is take the first thing, walk it down, then start over here, walk it back up, and you won't make a mistake. Okay? Does that make sense?
And you like do all your multiplying, and it's fine.
Right. So be careful if you have numbers in there, though. So like Kyle said, we're going to have 8x cubed here, right?
8x cubed plus 12x cubed y, then 6x y squared, and
Gotta call
y
mistakes,
cubed.
Katie. 6xy squared, there you go.
Plus y cubed.
We good? Make sure that when you do this part, you square the 2 and then multiply it by 3. Follow your order of operations, yeah. Gotta be careful with those. Should we do one more? One more practice one? Yeah.
Can we do something to like the 6? Can we please
Yeah,
let's do something
let's
in
do
6?
something to the 6.
Can we do x plus 7?
Not much harder.
X plus 7 in the 6?
Let's do different letters.
A and Z. A and Z.
Okay.
Or C and W for me.
Well, let's do one with minus.
Oh,
This is gonna be tough.
that's trash.
I said A.
That looks pretty tough. See if you get it. Write it down.
What's the sock doing in my backpack? I found the weirdest things in my backpack. Oh, I know why. I threw my laundry at my backpack. I know you're talking about me. Okay.
Oh, 7 more times.
Why?
I know you guys are talking about me. Uh-huh.
Careful of that minus. Careful with the minus.
Oh, I just have a question. Do you multiply 2 into the 6? Yes, you do.
So,
So 2, 6, 12. And then we'll do 15. So 3,
you need to use a calculator. I'm betting we do, unless we know our power tables very well. Some of us hopefully do.
and then we are 15, and then this is the dash 2, 6 to the big to the fourth. And here's your last. I'm confused.
I just had like 10 of them like this way.
Okay, how are you doing here?
I'm confused because the second one is driving me crazy. Can you add their coefficients? I'm confused.
Okay, couple more minutes. Hurry.
Yeah.
2x.
I was like, what do you
Kyle.
mean?
Hey, how did you find? I literally stopped using Z and started using Y. There is no Y. It's just Z, X.
I should have made this a candy bar problem, dang it. I don't have the answer right now though, so next time.
If I get the answer right, if I have the answer on my paper and I get it right, will I get a candy bar?
Other than X and Y, you get X3 and you have like big X.
Oh, you didn't pick a 2. It's easy to fix, right?
Yeah.
Cursive X.
4 times 6 is 20.
So are mine because they look different.
Should I multiply those two? A squared is 4. 4 times 6 is 24.
Okay, so go ahead and the powers on the right hand side.
X squared minus
Powers over there.
27 times 6.
Okay, I'm gonna start writing it on the board as we go. We do need to do some other stuff today.
62
So
Z cubed. What number is that?
Now these are messed up. Because we have 2 X's. We just have Wait, so
I'm
it'd be like
confused.
2
I got it wrong. Dang it.
see how you need a lot of room? Guys, give yourself enough room. I saw a couple people put it pretty close together. Oh yeah, I'm missing my X, aren't I?
Oh. Well, no, you have to do that to the 6. Oh,
Yes, we do.
I see that.
Okay, then I'm gonna need some calculator assistance. What's 3 to the 6th power, somebody?
Oh, 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 oh.
Oh, we should know that.
Yeah, it's like 729.
Okay, this is gonna get tricky. So we got 3 to the 5th power is 343?
243.
Oh, 243. Times 6 times, so it's minus, right?
Minus.
So what is that minus?
2,000.
What is it? I'm sorry. 916. Sorry. Z to the 5th X. Yes? There we go.
Y.
This one, is it going to be plus or minus?
Minus.
Negative, even power, plus. I think it's going to alternate, isn't it? It's like odd, even, odd, even. Cool. So we got 4, and that one is 81.
Yeah.
4 times 81, what's that?
It's like 700.
Times 15, who's got it for sure? I'm going to ask. 4860. Z to the 4th X squared.
There you go.
Yeah. We watching, Miss Crane, Miss Padula? Yeah, definitely you can. That makes it easier sometimes. Huh? Maybe we should. So this one we did, right? Okay.
Will we have any through the 6 problems?
Maybe one, I don't know. So let's see. Then this one we've got, I made a mistake here, right? That should be like that. So we got 27 times 20 times, this is going to be negative because it's odd. So times 8, what is that? 4320. Z cubed X cubed. That's like the middle term, it's both cubed. Yeah? Okay, we've got that one. Then this one is going to be even, so plus 16 times 9 times 15. Z squared X to the 4th. And then 2 to the 5th is 32 times 3 times 6. It's 18 times 32 is. Go ahead. Thanks for my calculator today. And this last one, oh, we can do that one. 2 to the 6th, 30 to 64, plus x to the 6th. There we go.
Homework due on Monday. That's not really participating.
That would be crazy to do, like expanding out the other way, right? It'd be tough to not miss it.
You should give us that homework, just this one big problem.
Yeah, just one.
Yeah, like something
All
to
or
the
nothing?
seventh.
Yeah, just to,
Yes.
to the.
No, I gave you a
So like
couple.
13.
but-
The 6th was.
Maybe I'll make that a challenge problem next week. Maybe I'll give you something like to the 15th power.
12.
No.
Make it worth something. Maybe worth money.
Make it worth a giant candy bar, because I need sugar. Or coffee. So I need lots of that. Can I have that coffee?
Okay, guys.
No, you don't.
So,
You don't need a coffee. You're crazy enough.
All right.
Are we playing?
Today we're also going to look at this. We're going to look at power functions, okay? So power functions are pretty simple. We just need to talk about them briefly. Maybe you look at them in our calculator and we'll be done.
Power
Alright.
functions, what are
So
those?
power functions are just monomials in a polynomial. In other words, things that look like x to the n, where n is an integer. That's a power function, okay? So we can split power functions into two cases, even and odd. When is n even, what's that look like? When n is odd, what's that look like? So when n is even, haven't we already studied one of those? So let's do odd, and let's do even.
Is there a difference?
Yes, there's a definite difference. They look very different. So n equals even, what would be the smallest even number?
2.
2. Well, actually, the smallest even number is 0 because it's even technically.
And it's
2. Yeah? Haven't we already done x squared? We already know what x squared
Yeah,
looks
it's a
like.
parabola.
It looks like a
It's
parabola.
a parabola
right?
that goes to 0,
U-shaped.
0, and it goes like, kind of like a U.
So maybe we should investigate another one today. Let's look at y
Fourth.
equals x to the 4th. Yeah.
It kind of looks like a
Okay.
It's parabola, right?
So, here's what I like you to do. Graph y equals x squared in your calculator and y equals x to the 4th at the same time so that we can compare them, okay? So put those both in your graph, maybe make one of them a different color, bold or something, okay? And we'll look at it up there too. So here's what I think you're going to find.
Could you do x squared squared?
Yeah, I'm done.
Will we die if we do that? It looks kind of like a scissor.
Okay? So we should have something that looks like squared.
Then we have like another one, which is kind of like weird, because it's like all weird.
Hey, what's the 4th degree one look like? Somebody tell me?
Kind of settles down.
Is it skinny or wider?
Here.
Wider.
It's a little wider, but it goes up.
It goes up quicker, it grows more quickly. So at the bottom it does something weird, but ultimately what's it do like at 1? Can you guys find where they intersect? See where the curves intersect. Find the intersection. I think it's like right here. Can you guys see that? You might have to zoom in. I think you'll see that x to the 4th does this. It's pretty clear to see that it grows faster. It is a narrower power function than x
We
squared.
need it 1, 1.
But what's it do underneath that?
It's shallower.
Yeah. I think it does this when you're between what two numbers?
1 and 1, because when you have fractions, numbers just get smaller and smaller, because fractions, when you square them or multiply them, they just get smaller.
Katie's absolutely correct. You guys know what she's saying? Let's like take a value. So if you take like 2 out here, if you square it, you get what? If you to the 4th power 2, what do you get?
Like 16?
16. So of course the red one is higher. You guys know what I'm saying? But what Katie's saying is if you take a fraction between 0 and 1, that's not true. Like let's take a value in here.
Half.
Yeah, something easy, a half. If we take a half and square it,
You get 1
square the top and the bottom, and you get a 4th, right? If you take a half and you take it to a higher power, like the 4th power here,
You get 1/16.
you get a
And
16th.
1/16 is smaller than before, so until it reaches 1 is smaller.
So the 16th is smaller, right?
Mm-hmm.
So hence this guy is going to be lower on the red curve than on the blue curve. So can you guys see that sneaky behavior? Other than that, this whole power functions thing is super easy. So higher degree is steeper as long as you're above 1 or above -1? Below -1. Let's see if we can write that. So this is one thing that we need.
Ooh, 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 ooh. It's like you write like
So for x bigger than 1, that's what you guys told me, right? How can we make this cover that way and that way? We learned that this year. Absolute value. Isn't that what that says? If the absolute value, if the magnitude is bigger than 1 in either direction, a higher degree power function is steeper or narrower, however you want to say it. Grows faster, all kinds of ways to say it, okay? That applies to even, it also applies to odd. So if we took like x to the 9th and x cubed, which one would grow faster? X to the 9th, except where? Except in this little neighborhood at the beginning, kind of, okay? So that would apply to even
nobody
or
likes
odd.
him.
Let's use some new notation and describe what's happening. We're going to talk about the end behavior. I'm going to write that down. End behavior. So, we want to talk about as we go to infinity. So, let's say as x approaches, that's what this arrow means. That arrow means approaches. So as x, this is the x-axis, right? As x approaches positive infinity, what happens to y for the blue curve or the red curve? What does y do? Y also approaches positive infinity. It's going up, right? How about this? As x approaches negative infinity, as we go this way on these curves, what happens?
Y reaches infinity.
Y reaches positive infinity still.
Unless it's upside down.
True, but we're going to just pretend it's not upside down. If it's upside down, they both go to negative infinity. But can you guys see how you write this with the arrow? We don't say equals, we say approaches. You can't equal infinity. Okay? You understand that? What kind of symmetry does this curve have? In fact, any even degree power function has the same kind of symmetry. Doesn't it have line symmetry? About the middle, you can flip it over and it's the same.
Mm-hmm.
So we can say line symmetry. Katie, you're going to have to chill. Do something about it. So, line symmetry about what? About right here, right? What is that? It's the y-axis, isn't it? About x equals 0? That'd be great. Let's do that one. About the line x equals 0 or the y-axis. Great, I think we're done. We know what we need to know about even functions. The only thing that's sneaky is in there. So be careful about in there, okay? But I'm sure you'll have a few questions on your worksheet to ask you about that. Odd, we could do the same kind of thing. Let's just think about a basic odd function. How about like x cubed? X cubed looks like that. I encourage you to graph some of them on your calculator. Maybe compare x cubed to something bigger. Okay? What kind of shape should we say it has? Snake. That's what I say. I always say it has a snake shape. Yeah? It does.
You know what I think
So
it looks
U-shape.
like?
I describe it better.
Snake shape.
It's like fladoodle.
That goes for x cubed, but it also goes for what else? X to the 13th, 21st, anything that's odd. Okay?
It's like wider.
What about
So-
27-1? What about x to the first power? That's great.
Yeah, x to the first power is kind of like an exception. So we're thinking like, good point. We're thinking like degree higher than 2. But doesn't it still do that?
It goes like.
X to the first power is a line. It still kind of has that shape, it's just not snaky, is it?
Is it like the same thing, like x to the 0 doesn't count?
X to the 0 would still follow the same end behavior rules as these other ones almost, so kind of does. Good question.
I have a question. So, like, snaky shape thingies, they have like a line of symmetry, like across like negative x plus y.
Odd number in the last
Hold on,
there.
you can answer in a second. Okay, end behavior.
Odd number in the.
You guys help me with the end behavior of this. So as x approaches infinity, what happens? As we're riding along the blue curve?
Y approaches positive ending.
No, it doesn't. You're going that way. Where does this say to go?
Infinity and
It
beyond.
does go out this way, right? Ride this way on the curve, going up. Not both ways.
As x approaches negative infinity, y approaches infinity. Negative infinity.
As we go this way, it goes down. Okay? That's how you describe end behavior precisely. And then symmetry. This one's got some different type of symmetry. I think it still has some though, right? Not all symmetry is just folding over a line. Some symmetry doesn't just go like this, because this one doesn't, right? Does it do this? I don't think it's a mirror image this way either. What does it do? It does something. It's got some kind of symmetry, doesn't it? So how can we describe it? I don't think it's line symmetry really anymore. It's kind of like diagonal maybe. Does it have... Okay, so we saw lots of functions like this, like logarithms and exponentials. Didn't they have symmetry like this? That was still line symmetry. It was just inverse symmetry. That's real key. But does this one have that? Is it flipped over both sides of my hand, if you can like think about it like that? I don't think so. Does it have like another part over here and then another part over there? It doesn't, does it? So it doesn't have any line symmetry. I don't think I can find any line. But it does have symmetry.
You make it sad sometimes.
If you plug 2 into x cubed, what do you get?
8.
How about if you plug negative 2 into x cubed?
Negative 8.
You get negative 8, right? Because it's odd, so it becomes negative. That would, if my curve was correctly drawn, it would go down here at negative 8. So that point and that point, there's something about those. Point symmetry.
It's point symmetry, except for it's all negative.
We don't want to just say point symmetry. Here we specified where, right? Let's specify what kind of point symmetry this has. What do you guys think?
Like the positive point symmetry?
Maybe like opposite point symmetry?
That's a good idea. Yeah, kind of.
Inverse or not?
Also a good idea. Using the vocabulary, very good. Across what? See how on that other one we said like we could say about or across that line?
It's about
What,
x.
across what
X
point?
equals negative y. Y equals negative x.
You can say across or about. Here, since it was line symmetry, we specified a line it was symmetric about, right? Here it's point symmetry, so we should be specifying a point it's symmetric about. What are these two symmetric about? Or these two, or these two, or these two, or these two,
The symmetric of across the origin.
which is 0, 0. Good.
No,
We
it's
see that?
like the 0.
You could have point symmetry for all kinds of other things across other points. I mean, it just depends what they are. For instance, don't all circles have point symmetry? Like if I draw a circle, we could study circles. We're going to wait till next year. But you could have a circle out in space and graph that circle. There's an equation for that circle, okay? What kind of symmetry does it have?
Like every
I think
single
it might
line of
have.
symmetry that you could possibly want.
Yeah, it has lines of symmetry, but it also has point symmetry, doesn't it? Across what point? This one?
No. Across the point in the middle.
Ah, across that point. So we could say that had point symmetry across that. Okay? Alright, I think that's all you guys need.
Cool.
So, here we go.
Do we have homework?
No.
audience.